How's your reproduction?
All right, it was good,
Yeah.
Yeah, we got my mother-in-law safely into an assisted living facility, which is
Okay.
just huge.
Wow.
It's life-changing after 3 years of having her with us.
Yeah, right.
With Alzheimer's,
Yeah,
we
right.
laughed as much as we cried, just because she would say things and do things that were just hysterical.
Mhm.
And it was like a comedy routine every day, because she's 90% deaf without her hearing aids.
Mhm.
And Deb would be yelling, you know, put in your hearing aids. And she'd be like, what'd you say? I can't hear you, you know? And we're just like, okay, you just can't write this stuff, you know? It's like,
Yeah.
all right, guys, let's get our cameras on. Hopefully some more people will show up here in just a moment. Right now, I'm only seeing Cosmo. There we go. Let's see these lovely faces. Okay, let's stand up. You're gonna want to stand up today a lot. You're gonna be standing up a lot today, okay? I think I probably could have performed a, well, probably taken wisdom teeth out of the previous people. I got them so punch drunk by the end of last class, yes. Come on in, guys, grab a chair. Okay, let's sit back down. Let's go through some nuts and bolts. What do we have on Friday? Quest, the final frontier. Nobody gets the joke, okay? Okay, quest. We have a quest. Quest number 5. Quest number 5 is on Friday. I was looking at over the weekend the content that I need to get through, and I do not think we're going to have a quest 6 before we have our final quest. So I'm going to need all the time to teach after Thanksgiving until those last 2 weeks. So that will be your last quest. Your final quest will be on final exam day. You know, like Dr. Warren, where can I find the final exam schedule? Google. Okay, you typed in JMU fall final exam schedule. Now you guys are a little weird because you're at Class starts at 9:45 and ends at when? 11. So we overlap which of the classes the most? Normally it would go 8 to 8:50, then 9:05 to 9:55, and then 10:05 to 10:55. So that's the slot we'd be in. That's the slot we'd be in the most. Okay, that's the slot we'd be in. That 10 to 10:55 slot. Okay, it will be run very much like the first quest, except no, we're not having any WebAssign. That was a horrible mistake. Okay, people not knowing how to put in vectors and so all that. So yes, so it will be a WebAssign. I mean, it will be a Canvas assignment that you guys will download and take. I'll give instructions later, but the department is insisting now that they want to record the Zoom anytime we give an online exam and make sure all cameras have people's hands in them as they try to hold down on accountability, hold up accountability on these things. Okay, but this doesn't matter, you'll be so busy, it won't matter. Okay, it's a final quest, it's not a final exam. It's a final quest, it's not a final exam. It'll be just like our other quests as far as lengths and times. Did you guys get my email? Did you get my email this weekend about the content and stuff like that, flashcards? If not, you might want to check your email, your JMU email. Okay, I've written down 3 definitions. Written down 3 definitions. So if you've just come in or you're just on there, you guys should write down those 3 definitions. Write down those 3 definitions. I'll get out of the way and I'll let you guys write them down. And also, if you just draw this drawing, we're going to pick up where we were. Draw this drawing over here. So that's the first thing. You'll all shut up and you guys can just write down these 3 definitions. I told them I got around 9 or 10 every time. They're like, no, you're probably getting 3. And I'm like, guys, I know I got more than 3 coming to class. I know I have more than 3. Somebody has a class of 60 and they have 3 show up. Just like, oh. Like, do you have a wide angle camera that they can't see either out of? Like, no. Like, well, what do you do then? Why post videos? Like, okay. Is that the new one, Cameron?
I've had it all year.
Yeah,
But yes, it is.
okay.
The other one is broken.
Nice. Okay, while you're writing it down, we'll read for you guys at home what we have here. We're defining in number 1 what it means to be a local MAC. Do we have this concept? We have this concept already in MAC 235. So when we're looking for global maxes, the same idea is going to hold. You're either going to be a local max or you're going to be an endpoint. But what do we mean by endpoint in 3-dimensional space on a space sheet? We'll talk about that later, not today. Did we talk about what it meant to be a critical point? Did we talk about what it meant to be a critical point in MAP 235? Okay? Either your derivative is 0 or your derivative does not exist. And that same idea is going to extend real naturally up to multidimensional space. So here we go. M, it's in the range. Notice it's in the range of the function. It's in the, what did I just say? Okay. M equals f of a is a local max. We say the local max occurs at a. Say that.
The local max occurs at A.
But it's f of a. That's the local max. That's what we're maximizing. Okay. It's a z value in my space sheet. It's a z value. Okay. Is a local max of f on D. D is the domain. D doesn't stand for derivative. D stands for domain. What does this stand for? What does this stand for? There exists. There exists, and then comes something out of Halloween, your nightmare. Delta greater than 0. And you're like, the only person I hate more than delta is epsilon. You're like, oh good, there's no epsilon, okay? Delta's by himself here. Okay, delta greater than 0, what does that stand for? Such that
The norm of x minus A.
whenever the norm of x minus a is less than delta, it implies that
F of x is less than or equal to.
f of x is less than or equal to m, okay? Now, right now, you don't understand anything that was said, okay? We're saying that whenever we pick an x such that the norm of x minus a is less than delta, it must follow that f of x would be less than or equal to m. Now, who's m in the game, guys? Who's m in the game? The local max, the z value. So what we're saying is, does anybody geometrically, this is when it just pisses me off I'm not giving a cumulative final exam. Does anybody remember geometrically what this shape is? The norm of x minus a is less than delta. Does anybody remember what that shape is? A circle. It's a circle of center at center A of radius delta. So if we're looking here, suppose my A is 2, 3. Suppose my A is 2, 3. What we're saying is there's some circle, there's some delta, there exists a delta where f of 2, 3, if this is the local max, there's some delta where this guy would be the biggest. And we can see on this space sheet, it's not a local max. If I'm thinking of this is slanting up like that. Do you see it's not a local max? And no matter how small you make this circle, there's always going to be somebody bigger in the circle than my f of 2, 3. Now, let's look at this shape right here. I just grabbed this. I didn't prepare for class, clearly. Okay, I just grabbed stuff from the hallway. Okay, if I'm looking at this right here, it says aluminum only. Okay, aluminum cans only. If I look at that, it does look like I have a local max right here. And you see, if you go down to the floor and we're looking at the domain, do you see how there would be a circle down here in the domain where this guy would be the biggest for everybody in the circle? He's the global max too, because he's the biggest of everybody on my surface here. He's the biggest of everybody on my surface there. Okay, so this is the definition of what it means to be a local max. Okay, now we're defining what it means to be the global max. How many people went to elementary school? Okay, hopefully some of you, I don't know, where'd you guys go? If you didn't go to elementary school. Okay, did you guys ever go have recess? Did they have recess? I don't know if they do. Do they still have recess?
Yeah.
Hopefully.
Okay, did you ever, how many people remember recess and did they ever have races? Did you ever get together and try to decide who's the fastest? This all just spurns. It wasn't like the teachers there setting up some kind of Russian, thing where run, you're going to decide who's going to go for your life, you're going to be in the Olympics, some communist thing. Okay, we're just saying you're just there and you're saying, okay, let's see who's the fastest. Well, when I was a kid, the kid who was the fastest at my elementary school was Chuck Treisler. And Chuck always finished probably 2 to 3 yards ahead of everybody else. And we just thought for sure this guy was a certain Olympic hopeful until we went to middle school, okay? And then we realized in middle school, us farm kids are not so fast. That's what we realized. Because first day of gym, Chuck got smoked. And all of us at Montgomery Elementary were like, was like seeing Achilles get shot in the heel. Like, Chuck got beat. Did you see that? Chuck, race again, because I came back. Chuck was hurt. And we realized, no, Chuck wasn't the fastest. But there was a neighborhood. There was an elementary school where he was the fastest. And we can imagine, like, you know, if we've got a space sheet, something like this, we could have two local maxes here. One like right here, and we have this one up here, where this would be like Chuck right here. He's Chuck right there. I feel like I'm a puppet guy now. Okay, and then we've got Usain Bolt. We got Usain Bolt up here, who's the fastest of everybody on the spaceship. He's the max of everybody on the space sheet. But notice, these bumps are not the maxes. The maxes are range values. So they're going to be values that occur over on the z-axis. This is where the m's going to be. They correspond to bumps on the space sheet. Okay. Now you're the global max, and this isn't hard. You're the global max of the domain of the space sheet, if and only if you're bigger than everybody on the... If your range value is bigger than everybody else, then you're the global max. You're the global max. You're the Usain Bolt. Now in business, do you think there might be applications where your boss may want to know such things as global maxes and global mins? Yes, in 2020 it's a little hard, right? I mean, I can't wait to see the mathematical models for 2020 in the stock market, okay? It's got... Okay. Now, definition of a critical point. Let's talk about what it means to be a critical point. First of all, we notice is that they're elements of the domain. They're down on the XY plane. You're a critical point in the domain, okay? If first of all, you're in the domain. I like to think of this as joining a fraternity, okay? You're joining a fraternity. Okay, you're a JMU fraternity. Anybody in here in a JMU fraternity? Okay, that's right, because you're engineers. And you're in a fraternity, it's called hell, okay? That's the fraternity you're in. Okay, misery, physics, misery, quantitative finance, misery. You don't have time for fraternities. But if you're going to be in a JMU fraternity, wouldn't it be good that you'd be a JMU student? You don't want somebody like me coming in and saying, I'm 60 years old. Can I join your fraternity? I'm going to pledge, okay? You don't want that. So first of all, you gotta be a JMU student, which means you've got to be in the domain of the function. If you're not in the domain, you're not a critical point. You're not a critical point. So if you kick the guy out of the domain, it's not a critical point. Then either the gradient is 0 or the gradient does not exist. Okay, which is just like, this is exactly like Calc 1. Either the derivative is
0
or the derivative does not exist. Now let me show you places where, remember, calculus is about, Dr. Warren, I'm barely awake. Calculus is about limits, derivatives, and integrals. Oh my, Dr. Warren, when are we starting integrals? Maybe Wednesday, if we're lucky. Okay, was the derivative defined in terms of a limit in this class? You have a quest coming up, okay? Do you think the definition of differentiability might be on there? If the limit as x approaches a of the absolute value of, I hate you, Dr. Warren, the limit equaled 0, okay? So what we can show is that if you have a corner point, if you have a point like this, we can show the derivative will not exist at that corner point. Just like in Math 235. Okay, because the limit's coming in one way, the tangent plane coming in on one curve is not going to be the tangent plane that we have here. And we know that gradient vector represents the first two components, talks about the gradient of my thing. Where if I'm on a nice smooth thing, let me put this back on. Maybe I use my fist. Here the tangent plane, if I'm nice and smooth, the tangent plane's gonna sit and rest. All the limits will be the same, all the limits will be the same. So at corner points on the surface, we lose, differentiability. Is that still, if this represents profit, if this is your profit sheet, is a corner point still interesting? Is it still an interesting point? Is that still a maximum? It's not the model you were hoping for. If it looks like this, guys. A witch's hat, okay? Is that still an interesting point? Is there a z-value corresponding to it that you could mark? It's just we've lost differentiability. We've lost differentiability there. Okay. All right, stand up, stand up, stand up, stand up, stand up. Stretch. We're going to test your memory to get you ready for Friday. We're going to test your memory. Sit back down, sit back down. Now, all you'll be doing on Friday, what did I just say? Is getting back a quest and taking a, I'm not going to teach you on Friday, okay? So you just need to come in, take your quest, and get out of Dodge. Okay, that's all you need to do. Come in, take your quest, leave with your quest, and get out of Dodge. Guys, I'm really struggling with COVID, and you know, if somebody has the flu, they don't know if they have the flu or have COVID. They can't take my quest. I'm struggling getting everybody assessed, and I'm struggling more being able to have times, opportunities to get stuff physically back to you. So I may just have to post grades for the first time, and probably only time in my life. I may start using Canvas. Okay, so I may start posting things to Canvas. If I find a couple hours just to enter all the data, I'll try to do that. Or I'll try to write some script to try to do it for me, which would take longer in the end, but will be more satisfying. Okay. This is a space sheet. I say space sheet, you say z equals f of x, y. This is where we were, this is where we left off on Friday. We got a point in the domain which is 2, 3. We've got a point in my domain which is 2, 3. The coordinates of this point on the space sheet would be, 2, 3, f of 2, 3. Okay, how many people drew that? Okay, draw you pointing down in the domain away from 2, 3. Draw a U down in the domain away from 2, 3. Draw a line that goes through 2, 3 and runs in the same direction as that U. Now you're gonna hate me. Imagine that I evaluated the function along that line that you just drew. It's going to create a space curve up on your space sheet. Do your best to draw that space curve underneath your line up on your space sheet. I'll do the same thing, I'll catch up. You might use a little long. Okay, there's my unit vector pointing in the U direction. What did I ask you to do next? Draw a line down here in the domain. There's my domain curve. What did I ask you to do next? So I know it's going to run through 2, 3. It's going to come down here and maybe do something like that. How many people are following so far? Okay, what would be the vector valued equation of that? What would be the vector valued equation of that space curve that you just drew? It's a vector valued function in three-dimensional space, so it better have an x of t, a y of t, and a z of t. Can you figure out what the vector valued equation of that curve would be. When I say line, you say
A plus
A plus TD. Okay, I should really have you cheat, look around. This is when I miss having my students in class. You guys, does anybody have any idea whatsoever what the first vector valued function would be? 2 plus TU1. The first component of my line, A plus TD. What's the next component?
3 plus TU2.
So that would position me on this line. How do I get up to the surface? How do I get up to the surface, guys? Evaluate your function, evaluate your space sheet at these two things. So it'd be f of
2 plus TU1.
and then
3 plus TU2.
how many people are following? How many people are following? Okay, then what we ended class with was a fast way to calculate this. I'm gonna write it down and you're gonna tell me what I just wrote down. Ready, Robert? Here we go. This does not stand for domain, it stands for derivative. Now we've got a vector, then we've got an f, and then we're going to have 2, 3. This was in the upper board on the right last time in class. This stands for the directional derivative in the direction u of f at 2, 3. It was defined in terms of a surprise. I mean, yes, it's shocking. It was defined in terms of a limit. But how many people do not want to use the limit to calculate the derivative? When it was all said and done, we showed that this was equal to, a fast way of calculating it was equal to the, how many people? What is that symbol? The gradient of f at 2, 3 dot product dotted with the unit vector u. How many people think that you might be calculating directional derivatives on Friday? I mean, if you just had to guess, how many people think you might be? How many people might guess you might be calculating? Now, what does the gradient stand for, guys? What vector is the gradient? At 2, 3, and then the, and then we're just dotting it with U1 and U2. I'll give you the U's. You won't even need to turn them into unit vectors. Your boss won't. Your boss will say this direction. But I'll give you the unit vector. How many people are like getting more comfortable taking partials? I mean, how many people are getting more comfortable taking partials? Okay. Now imagine that. Okay, no. Stand up. I felt the boredom just seeping around the room. And at home, I can't imagine what it's like. You're all so bored. I had one person in my last class with 6 dogs in the grid. I'm like, what are you running, a shelter? What makes it seem like a good idea to show up to class with 6 dogs? I'm picturing like if you actually showed up, these are my service animals, my comfort animals. Sorry, sit down. I'm not kidding. Yeah, I'm too old. Okay. Here we go. Somebody in the last class said something I never heard before. And I don't know if you've ever heard this either. I doubt Michael has. Okay, He said, let her rip tater chip. Has anybody ever heard that saying before? I'd never in my life, I'm 60 years old, I never heard, what did I just say? Yes, that's just you guys. I mean, none of you in the grade said anything. Robert, your mouth didn't move at all. What did he just say? Let her rip tater chip. I'm like, you've got to be from Southern Virginia. You got to be down there near the Danville area to come up with that one. Okay, so you grew up eating to stop. Okay, I like it. Okay, back to where we were here. If I'm at 2-3, imagine that I'm at 2-3. This represents how the space sheet is changing in the direction of u. So if I'm looking in the direction of u, this is describing how the z is changing, how my space sheet is changing. Does this seem important? Does this seem like this is an important idea? Now imagine I ask the following question. Out of all the directions u I could go, if I use this as a compass, out of all the directions u that I could go, where will the space sheet be immediately changing the most? Does that seem important? If I think about using this u as a compass, this unit vector as a compass, I'm saying, where could I point this thing? Where could I point this thing so that the z value would be increasing or decreasing the most as I immediately walk away? And so I want to argue right now, we can find that. We can find that. So we look here. We know that this is, read it to me, the directional derivative in the direction of f z at 2-3. But we can calculate that by taking the gradient vector and dotting it with the unit vector. Now, let's go back again. This pisses me off. I'm not giving a cumulative final. Does anybody remember another way to geometrically calculate a dot b, or what a dot b is equal to? Does anybody remember from their gray matter what a dot b is equal to?
Norm of A times norm of B cosine beta.
Perfect. Norm of A times norm of B times the cosine of theta. How many people remember that now? How many people remember that? What the hell's theta's job? Who's theta in this game? Who's theta in this game, guy? Who's theta? The angle between A and B. So sitting here, here's A, here's B. Where would theta be? Where would theta be? Something like that. So now let's come over here. Let's come over here. The directional derivative is this, but this is a dot product. So now I've kind of run out of space, so I'm just going to run up here. But this would be equal to the norm of A, which would be the norm of the gradient vector, evaluated at 2-3, times the norm of the unit vector, times cosine of theta, where theta is the angle between them. So I'm down here, guys. Notice how many components. I could have said whatever. Nobody would listen. I don't know how many components are in the gradient vector. Now you listen. I mean, you couldn't hear. How many components are in the gradient vector? 2 components. So it's a vector down here in the domain. So it's not a unit vector. So it's longer or shorter than this. This would be like the gradient vector at 2-3. Now where would theta be? Where would theta be? Where would theta be? The angle between the gradient vector and the unit vector. Are you following? Are you following? Okay, but what is the norm of a unit vector? 1, so let's just, you can't do this, but I can. So then the directional derivative is just the norm of the gradient times the cosine of the angle between the gradient and the unit vector. Okay, now at home, I want you guys to do your best. What does cosine look like as a graph? I mean, let's do it. What does cosine look like? What does cosine look like? And you go, okay, how many people like, this is all we really know, okay? What's the highest it ever is? What's the highest it ever is? 1. What's the lowest it ever is?
-1.
-1. So I'm looking at this cosine. What angle down here would give you the 1? What angle would make cosine return a 1?
0.
0. If this is 0, the cosine of 0 would be 1, which is the largest value that I could get here. Like type 1, what does that mean? Well, it means when you put your unit vector in the same direction as your gradient vector, that's going to point to the greatest change. So if you think about your gradient vector, how many people can calculate a gradient vector? How many people can, I mean, like, if I gave you a space sheet, how many people think they could probably do a pretty good job at getting fx at 2, 3, fy at 2, 3? If you use that as a compass and you step away from 2, 3 in your gradient direction and you look up, that should be the direction of greatest change. Imagine that this space sheet represents energy in a physical system. Imagine this represents energy. Then if I'm moving away from 2, 3, that's where I would expect the energy to increase the most. Is this useful? Do you think this is useful? Now, what angle would give you the -1? What angle would return a -1? Think about your unit circle. What angle would make cosine -1?
180 degrees.
180 degrees, or pi. So if I swing my unit vector, just opposite the gradient vector, that would be point in the direction of greatest increase. What's the director that's oh my gosh. English is coming. I'm gonna fog you up. Do you see that? Wasn't that fun? Okay, you wouldn't focus anyhow. How do you find the opposite direction of a vector? As the train whistle blows. How do you find a vector that's opposite direction of a vector? Multiply by negative. So the gradient of f points in the direction of greatest increase, but minus the gradient points in the direction of greatest decrease. Points in the direction of greatest decrease. Do you think that could be on the quest? I'm just wondering. Do you think that might be? But it all went back to this geometry that we had. Okay, stand up again. You guys need it, I can tell already. Stand up again. Stand up again. Stretch. Stretch. Stretch some more, stretch some more. Okay, sit back down. Time to go back to art. Dr. I hate drawing. Draw yourself an XYZ. No, I'm not doing it. Draw yourself an XYZ. Okay, mark a 2, 3. Mark a 2, 3 down in your domain. Okay, now, to the best of your ability, I want you to draw a space sheet. Don't draw anything yet. Draw a space sheet whose top looks like a mushroom. Draw a space sheet whose top looks like a mushroom. So try to draw a mushroom. Without the stem, just the top of the mushroom. Okay, now artists, draw a U that points away from 2, 3. A unit vector that points away from 2, 3. Now draw a line that runs on top of that unit vector. Okay. The top of your mushroom should be at 2, 3, f of 2, 3. The very top of your mushroom should be at 2, 3, f of 2, 3. Now you're going to hate me. Try to draw the space curve that results from evaluating the mushroom on that line 2, 3 plus t, u1, u2. Dr. Warren, certainly we're done. No, we're not. How many people have that line running through the top of their mushroom? How many people have that running through the top of their mushroom? Draw the tangent vector to that space curve at the point 2, 3, f of 2, 3. Draw the tangent vector in your art. Some of you aren't drawing anything. Okay, now to top it all off, this is the cherry on top. Draw the tangent plane that holds that tangent vector, the tangent plane to the point 2, f of 2, 3. Okay, now I'm going to catch up. What was the first thing I asked you to do? Draw an XYZ. So I'm going to do that over here. What was the next thing I asked you to do?
Mark a 2, 3.
How many people got there? What was the next thing? And this was the hard part. What was the next thing I asked you to do?
Draw a unit vector.
Did I have you draw the unit vector or the mushroom first? I forget. The mushroom, somebody goes straight up. That's going to be the top of my mushroom. I should have told you that. That doesn't really look very straight. Okay, so now I've got this mushroom. Like, Dr. Warren, how do you draw a mushroom? I don't really know. Let's just make it go like that, maybe. And then we'll just give it some kind of like, something like that. It goes in the back. Does that kind of look like a mushroom? Does that kind of look like a mushroom? Then what did I ask you to do? Unit vector. And I don't know why I kind of like mine sticking off like this. Then what did I ask you to do?
Draw a line.
Draw a line. Then what did I ask you to do? Draw the space curve. Now since it's going through this point, and the way my line's going, I'm thinking I'm not going to be able to see it behind here. So I'm going to use a dotted line. To kind of represent that. That's kind of like what I can't see. Now, as I come through the point 2, 3 down here in the domain, I'm here, and then I'm going to ride Cameron's, what's that thing called again, Cameron? What is it? A one wheel, okay. Cleverly named. I'm going to ride Cameron's one wheel, but I'm going to be riding down the front here of my mushroom. So I'm thinking this is like my space curve. And it's going like that. Did anybody else get art that looks something like that? Now, what was the cherry on top? Oh no, then what did I ask you to do? Tangent vector. Since I'm running in this direction, my tangent vector is going to go right at the very top. So I'm thinking it's going to be like that maybe. perspective, maybe something like that. That's my tangent vector. And then I ask you to do what? Then I ask you to do what?
Draw the tangent plane.
Draw the tangent plane. That maybe contains it. Did anybody get art that maybe looks something like that? Now, instinctually, guys, instinctually, what does it look like the tangent plane should be doing if it's the top of the mushroom? If you think about it, you're up here at the very top of the mushroom. What does it think like the tangent plane that holds all the tangent vectors?
That's flat.
Does it seem like it'd be like at that angle there? Does it seem like it'd be at that angle there? Or like that angle there? How does it seem like it has to be? How does it seem like it has to be if you're at the very top?
It's flat.
Dead flat. Does that make sense? Does that make sense? If we're at the very, I've got the top of the mushroom, and I'm at the very top, that tangent plane is going to have to be parallel to the
That's flat.
XY plane. Okay, it's Friday. I ask you to find the tangent plane, the equation of a tangent plane. What's the flashcard? I hate you, Dr. One. What's the flashcard? If you were looking for the equation of the tangent plane to the surface at 2, 3, what's the flashcard? Very good. Z minus f of 2, 3 equals
Partial derivative x minus.
times. Am I done? Am I done? Am I done?
That's not what-
Plus, which is disappointing. Where'd that come from? The dot product. Fy at
2, 3.
2, 3 times
Y minus 30.
y minus 3. How many people might want to have that memorized by Friday? How many people might want to have that? I'm not seeing anybody's hands in the grid. You guys, Sean, I'm not seeing your face at all. Brandon, are you there? Brandon, yeah, okay. Luke, are you there? Luke? Yes, okay. All right, here's a tougher question. What was the simplest normal vector? I say plane, you say, I hate you. I say plane, you say n dot x minus a equals 0. Well, it's pretty clear the A is the position vector 2, 3, f of 2, 3. There's your A. Does anybody remember what the normal vector that gave us, does anybody remember what the normal vector was that gave us this equation? Da da da, oh, poor Jeopardy.
It was the cross of you take 2 tangent vectors. And this
That's
is
the way we got it, yeah, that's the way we got it, Gordon. But we factored something out, and we said, we factored out that U1, U2 minus U2, U1. What was left on the inside? Does anybody remember the last component? 1. Does anybody remember the other 2 components?
The negative partial derivative with respect to x. At 2, 3.
Minus the partial derivative of f with respect to 2, 3, and then
The negative partial derivative with respect to y at 2, 3.
negative partial derivative with respect to y. That's very good, very good. I won't read that. Okay, so now imagine that I've got my tangent plane and I've got my normal vector. Here's my normal vector. What's the equation of my normal vector? Okay, no, seriously. What's the equation of my normal vector? Negative partial and then negative partial and then 1. Okay, so now imagine that I've got my tangent plane and I've got my normal vector. Okay, you tell me when I'm going to be on top of the mushroom. You tell me when I'm going to be on the top of the mushroom. When am I going to be on the top of the mushroom? Right now. What do you notice? What do you notice about this vector?
Pointing straight up.
It's pointing straight up. What's the only way a vector can be pointing straight up?
It's a cross product of the.
Yeah, it's pointing straight up. It's pointing straight up. So how far would I go in the x direction?
0.
How far would I go in the y direction?
0.
And then pointing straight up means I'm going that far in my z direction. So we know our normal vector has this form. We know our normal vector has that form. But I want it to point straight up. I want it to point straight up. So what would that value have to be?
0,
And what would that value have to be?
0.
And so what we see here is that if the gradient at 2, 3 is the 0 vector, if both components have to be 0. If the gradient at 2, 3 is 0, then would that be 0? Then would that be 0? Would that be 0? Dr. Warren's got a minus. It's a 0. Would that be 0?
Yeah.
And would that be 0?
Yes.
Okay, so here we go, guys. Beautiful result. If you have a local max, your tangent plane is going to be parallel to the domain, which would mean the gradient would have to be.
0.
So if the derivative is 0, you could have a local max or local min. The same result extends from 235. If you're looking for local maxes and local mins, you're looking for places where the derivative is 0, except now it's a 0 vector, or we have a corner point. We have a corner point like this. We have a corner point where the derivative would not exist. You'd have a place where the gradient, where one of these two does not exist. Does this make sense? Does this make sense? Isn't this a beautiful extension from Math 235? Dr. Warren, I don't know what you're talking about. You should know what I'm talking about. Okay. So you're looking for local maxes and local mins. I gotta ask, guys, if you have a mathematical model, do you think your boss might want to know where it takes a maximum and where it takes a minimum? I'm just wondering, do you think that might be useful?
Mm-hmm.
How many points are in the domain? I just erased my drawing, I can't believe. Oh, how many points are in the domain? How many points are in the domain to check? Infinitely many. Does that sound like fun? Does that sound like the fun way to do it? Let's just check them all. Do you want to graph the space sheet? You're like, Dr. Warren, I'm not even sure how to do that. I kind of know a little bit from that graphing routine. Do you think you're going to plot it and say, oh, I think the max is there? What's another way? Take the gradient and find out when it's equal to, find all the x, y values that will make the gradient equal to 0. Those could be potential local maxes and local mins. Now, let's draw x cubed. Draw x cubed. You mean, Dr. Warren, like just high school? Yeah, high school. Draw x cubed. Draw the graph of x cubed. What does the graph of x cubed look like? What is the graph of, you guys help me out, what is the graph of x? What does the graph of x squared look like? Let's go back to something we actually know. What does the graph of x squared look like? And we're like a parabola. X cubed looks like a snaky thing. It comes up, goes flat here, and then goes back like that. That's the graph of x cubed. How many people can take the derivative of x cubed? I mean, I'm just wondering. If you can't, we probably shouldn't show up on Friday. How many people can take the derivative of x cubed? If f of x is x cubed, how many people can take the derivative of x cubed? 3x squared. What would the derivative of x cubed at 0 be? What would the derivative of x cubed at 0 be? 0. So the tangent line looks like that. Is this a local max? Is this a local max? No, there's no neighborhood where it's the biggest. Is it a local min? No, there's no neighborhood where it's the smallest. So just because the derivative is 0, does that mean it has to be a local max or a local min? No, and the same is true when we jump up to higher dimensions. Just because the gradient is zero doesn't mean it has to be a local max or a local min. Like, well, Dr. Warren, could you give me a shape that maybe looks something like that, where I wouldn't have a local max or... Who's ever ridden a horse before? Who's ever ridden a horse? Nobody? No? Okay, a couple people. I saw Raylan. Raylan's ridden a horse. When you ride a horse, what do you sit in, guys? What do you sit in? A saddle, okay. How many people are glad at that center point where your butt sits that it's not a local max? How many people are glad it's not a local max? That your saddle doesn't look like the top of an egg. How many of you are glad that that's not what your saddle? Would that be an uncomfortable ride? Would that be an uncomfortable ride? How many of you are glad it's not like a local man? Could you imagine sitting in that saddle with your legs like this, up like that? How many people like be disappointed if that was the saddle ride? Could you imagine riding you're riding with your legs up like that, and your legs up like that, and your butt's down in the saddle, and you're going. I guess that would actually be kind of a funny show. I mean, but I'm looking at that there. When we're thinking about a saddle, it goes kind of up in the middle, but as you come around this way, it goes down like that. So we have a nice place to put our legs. And then we're riding here so we don't fall off the front or the back. And so we call these places where the gradient's zero. Right here, I would still have a flat tangent plane. But my legs are sitting right there in the middle. We call these kind of points where we don't have a local max, we don't have a local min, we call those, cleverly enough, saddle points. We call them saddle points. Doesn't make sense why we call them saddle points. So if the gradient is zero and you don't have a local max or local min, you have a saddle point. You have a saddle point. Oh. Stand up. Stand up. Stretch. You need to stretch. You've got Doug coming. Doug's coming. Okay, I'm just letting you know. Doug's going to take you out and duct tape you. Okay, you're going on playing Japanese concentration camp. Stretch, stretch, breathe, look at somebody and say, wake up. Don't breathe on them, just say, wake up. Okay, let's sit back down. So Dr. Warren, how do I possibly find out if it's a local max or a local min? You said it's important. How can I possibly do it? Well, you're not going to like it. I'm telling you right now. Here's one option. Okay, well, here's one option. We just test every single point around here. How many people think that sounds like a bad idea? How many people think that sounds like a bad idea? Okay, another way is we become clever. That doesn't sound good either, Dr. Warren. That sounds like I won't understand. Okay. How many people think they could find the equation of the space curve that you drew? How many people think they could find the equation of that space curve that you drew? And what would that equation be? We've already written it down once today. What would that equation be? 2 plus TU1.
3 plus TU2. F is 2 plus TU1. 3 plus TU2.
How many people are following me? How many people are following me? Now I've got to ask. This line down in the, is it a domain curve? Is it a domain curve? Is there an actual value of t that would hit 2, 3? What value of t would you put in there to hit 2, 3?
0, 0.
0. So if you look at R of 0, if you evaluate this space curve at 0, at t equals 0, what do you get from the first function? What do you get on the first function?
2,
2. What do you get in the second function?
3.
And what do you get on the third function?
F 2, 3.
So it does hit our local max. The curve runs through our local max. Now we know the tangent vector points in the tangent plane, which we're saying, since it's the top of the mushroom, has to lie flat. So it's up here in this flat tangent plane. Do you guys remember how to get tangent vectors from space curves? Again, we're not taking a cumulative final, which just horrifies me. If I give you a space curve, how do you find the tangent vector? The derivative. It points in the direction that the curve is going. So let's take the derivative of this. No, Dr. Warren, let's not. Let's not take the, no, let's take the derivative of it. Let's go ahead. Let's take the derivative of this. R prime of 0, that would be this tangent vector. R prime of 0, that would be the tangent vector. Okay, you guys get the first two components. You guys find the first two components in the tangent vector. R prime of t. You guys get the first two components. And this is when the 6-foot barrier just pisses me off. Okay, what would the derivative of x of t be? What would the derivative of this first vector value function be? Just u1. This is 0. u1 is just a constant, so I just get a u1. How many people are happy so far? How many people are happy so far? Like everyone got this. How about the second component? u2. And now it's the third component. And you're like, oh crap. I'm going to need something I'm going to need on Friday that we derived in here, which is called chain rule. If a function is pregnant with twins, what's the derivative of the function? Am I done?
Times the derivative of x of t.
Am I done?
Plus
That,
partial of f of y. Times derivative of y of t.
times the derivative of y of t. Now let's look up here. We're in here. Who's my x of t?
2 plus t1.
And who's my y of t?
3 plus t2.
So you guys use the chain rule and get the derivative. You guys use the chain rule and get the derivative of that third component. So I have the partial derivative of f with respect to x at times u1. Since u1, u's just a scalar, it's just a vector, so it would just be times u1. Then I would have a plus
Partial derivative with respect to y.
then times u2. How many people are following? But guys, the tangent plane is flat when the gradient is,
0.
0. So if you're looking here, the gradient r prime of 0, you guys help me out, r prime of 0, if you evaluate this at 0, you would get a U1, nothing's changing there, U2, and then I would get
Partial derivative of
2, 3 times U1 plus times
U2.
U2. Now suppose the gradient at 2, 3 is 0. Then this would be the gradient at 2, 3 is 0, then that would be a
0.
0. This would be a,
0.
so the third component would be a
0.
0. So I would just have my third component being U1, U2, which is down here, but I've just moved it up to there. Is this vector lying in your tangent plane? You know, that's not the question. The question was, how do I know if it's a local max or local min? And I said, well, we could test all the points. You're like, no, we're not doing that. And I said, well, we could be clever. Gordon said, the derivative points in the direction the curve is changing. Does it make sense that u points in the direction where this thing is changing, where the curve is changing? Geometrically, what does that tell me? Not physics, that's acceleration, I get that. But geometrically, do you remember on your final exam that you're not taking, what the second derivative with respect to t represents? What's your name again?
Patrick,
Patrick, say that again.
where the curve is curving.
Come on up, Patrick, say it to the camera. Come on up, Patrick, say it to the camera. They're tired of seeing me.
The second derivative is where the curve is curving.
Did you hear Patrick? How many people heard him? Did you guys in the grid hear that? Let's give it up for Patrick. Let's give it up. I want to see your little hands clapping in the grid. I want to see hands clapping. Okay, I guess snapping. I don't know what snapping. My daughters snap a lot. Never for me. I'm just like, this is what my daughters do to me. Seriously, Dad, seriously. You want to know something? I'm going to have a little bit of like, you know, it's okay for them to get with their friends and giggle and laugh and make fools of themselves. But the moment I start playing around and laughing, it's like I'm the dad, and it's like they look at me like I've got mad cow disease. They look at me in horror, like, Dad, stop. Dad, stop. Quit being silly. Dad. I don't want to, that could be hereditary. Stop. I'm like, you were just making a complete ass of yourself just a moment ago. It's okay for you to be fun, but not me. I can't be fun. They'll sit and sing in the shower, la la la, whatever popular music it is. But if I sing, Dad. Yeah, no. Just pay the bills. Pay the bills. You're forgetting your job here. Your job is to pay the bills, not to have fun. You pay the bills. Okay, but back to where we were. All right. Patrick said the second derivative describes how the curve is curving. Okay, so the second derivative describes how the curve is, describes the direction the curve is curving. So if we're on a space curve, and we're coming around like this in three-dimensional space, and I'm looking at this, that vector would be my tangent vector. That would be like my r prime at whatever value of c I'm at. How many people are following? How many people? Now, where would my r double prime be? I mean, if we're sitting here and we're looking at this, where would my r double prime be? Where would my r double prime, as the vector r double prime? Would it be pointing out like that? Would it be pointing out like that? No, it's going to be pointing in like this, maybe. We're not sure how it's going to be. Remember the T in B plane? You guys remember that? No, Dr. Warren, I hated that. Remember the T in B? This would be the direction of T. This would be the direction of N. And then t cross n would be, in this case, b that would point down there like this. R double prime is in the direction of n. R double prime is in the direction of n. But R double prime, as Patrick said, points in the direction the curve is curving. Now, I know you're going to be pissed, and we're not going to have time, but we're going to do our best. Here's the first derivative. How many people are with me there? Let's take the second derivative. And you're like, Dr. One, maybe. Maybe these first two components, yes. But this, hell no. Hell yes. Let's start off. How many people are pretty comfortable with the first two components? There's only three. What's the derivative of the constant u1? 0. What's the derivative of the constant u2?
0.
Okay, and then we're stopping right there for a moment. We're stopping. Okay, that means x is 0 and y is 0. So the vector's either pointing straight, up, or it's pointing straight down. It's either pointing straight or it's pointing straight
Down.
So imagine that it's pointing straight down, then the curve is curving down. Imagine it's pointing straight up, then the curve is pointing up. And you're like, Dr. One, we're done. All we gotta do is check the second derivative and to see if it's going up or going down. And I'm like, oh yeah, no, those saddle points. Could there be use in a saddle where it might be going up? If you've ever ridden a saddle, you hope so. Are there also curves where you'd be going down? So here's the moral of the story, and you're not going to like it. If it is a mushroom, if I have a local max, then the second derivative always has to be pointing down. The second derivative would always have to be negative. Now here's the kicker. This is the thing that's going to piss us all off. For every direction, u. Dr. Warren, no, we're not doing that. We're not checking every direction u. And you're right, we're not. But we're going to have to get clever. We're going to have to get really clever to not do that. And to do that, I need you guys to help me. You guys are going to have to take the derivative of this mess. You're going to have to take the derivative. Now u1 is just a constant. u2 is just a constant. But these functions ain't constant. So you guys are going to help me. Suppose I've got apple, Dr. Warren, don't you dare. Suppose I've got apple of x of t. Any function of x and t. Could you take the derivative of that? It would be apple x evaluated at times x prime of t. Am I done?
Plus partial derivative of
Apple y times
x of t y t
times.
y.
So we'll do this in a little part. The u1 we're not going to worry about. This will be my first function. Who's the apple? Not f. Look what's there. F of x is the freaking. Who's the apple? F of x. So if I wanted to take the derivative of apple, now I'm going to put in this 2 plus t u1. Don't you swear. 3 plus t u2. It would be apple x, but I already have one partial derivative, so it would be not the movie channel fx, but the movie channel fxx. Does that make sense? It would be fxx at, oh, I hate you, Dr. Warren, at, am I done, times x prime, but what's x prime? U1. Am I done? No, you write down the second term. I've done enough work today. You write down the second term. Okay, what do you guys have for me? What do you 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 have for me? fxy, partial derivative with respect to x, then with respect to y, evaluated at, I'm gonna have to write really small, you guys are gonna have to listen well in the grid. 2 plus tu1,
3 plus TU2,
3 plus tu2 times
U2.
times u2. How many people are following? Okay, that would be if I took the derivative of this. Ignore this u1. Ignore this u1. Now you guys write down the exact same kind of process, but if we took the partial derivative with respect to y. We took the derivative with respect to y. The derivative of the partial derivative with respect to y. If apple is fy. Okay, for sake of time, because this class is gonna have to end, we would have fyx at, and I'm getting lazy now, okay? Then times u1, am I done?
Plus. Y.
u2. Now, guys, we're gonna start with this on Wednesday. But notice, we don't have this U1 in the game yet. We don't have this U1 in the game yet. And we don't have this U2 in the game yet. These U1s and U2s that are up here are coming from using chain rule again. Here is Claret's, do not write it down. I can't even spell it. Claret's theorem says the following. Claret's theorem said the following, that as long as your partial derivatives are continuous, what is that? What did I just say? What did I just say in the grid? I want to see your mouths moving. What did I say? Then it doesn't matter if you take the partial derivative with respect to x, then the partial derivative with respect to y. It would be equal to the partial derivative of y with respect to x. This is Claret's theorem. And for your functions, it will always hold. Okay, we'll pick up with this soap opera. On Wednesday. You have what on Friday? West 5. Thanks, guys. Thanks for coming to play.